3. iAtlas isn't your typical space rock. July 1st, 2025, the Atlas telescope in Chile spots something moving fast through the constellation Sagittarius. Too fast, moving at 61 kilometers per second relative to our sun. That's 220,000 kilometers per hour. No asteroid moves that fast unless it came from another star. Within days, telescopes worldwide confirm it. This thing came from interstellar space. Only the third visitor we've ever caught in the act. 1. Oumuamua in 2017. 2. Borisov in 2019. Now 3. iAtlas. But this one's different. This one's heading straight for Mars. October 3rd, 2025. Mark your calendar. That's when 3. iAtlas passes just 29 million kilometers from Mars. Close enough for NASA's Mars Reconnaissance Orbiter to snap pictures with 30-kilometer resolution. Close enough to see what this thing really is. Because after 3 months of observations, scientists can't agree. Natural comet or something else entirely. If you value documented space exploration history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. This script is researched and factual. Using sources from Harvard's Institute for Theory and Computation published in August 2025, and NASA's official 3 iAtlas research documents published through September 2025. Now back to the information. You're looking at something that shouldn't exist. Current models predict we should see maybe 1 or 2 large interstellar objects per year maximum. But 3. iAtlas measures somewhere between 440 meters and 5.6 kilometers across. That makes it potentially the largest interstellar visitor we've ever detected. The odds of finding something this big, astronomical. Avi Loeb at Harvard thinks those odds are too long. In his paper, Is the Interstellar Object 3 iAtlas Alien Technology, published July 16th, 2025, he argues the trajectory is too precise. The object will pass just 2.7 million kilometers from Mars' orbital path. That's like threading a needle from another star system. Random trajectories from interstellar space have a 1 in 500 chance of aligning this closely with our planet's orbital plane. But here's what makes October 3rd critical. As 3 iAtlas approaches Mars, 2 things happen simultaneously. First, the high-res camera aboard Mars Reconnaissance Orbiter gets its best shot, 30 km per pixel resolution, sharp enough to separate the nucleus from surrounding dust, sharp enough to measure the object's true size. If the core turns out smaller than expected, that changes everything about its nature. Second, 3 iAtlas enters what NASA calls solar conjunction. It disappears behind the sun from Earth's view. No ground-based telescope can observe it during the critical perihelion approach on October 29th. Mars becomes our only witness to what happens when this object gets closest to our star. The Webb Space Telescope caught something strange in August. 3 iAtlas doesn't behave like other comets. Its coma, that fuzzy cloud of gas and dust, is 87% carbon dioxide. Most comets are dominated by water vapor. This thing is breathing out CO2 like an industrial furnace. Webb also detected traces of carbon monoxide and cyanide. Plus something unexpected, nickel without iron. That's not how nature makes metal. That's how we make nickel alloys in factories. The Hubble Space Telescope revealed another anomaly. 3 iAtlas has an anti-tail pointing toward the sun instead of away from it. Comets don't do that. Solar radiation pressure pushes material away from stars, not toward them. Yet there it is in Hubble's July 21st image, a bright extension stretching sunward like the object is somehow drawing material in the wrong direction. Then there's the polarization data. Published September 9th by researchers studying 3 iAtlas's light signatures. The object shows extreme negative polarization values, unlike anything in our solar system. Its surface reflects light in ways that don't match known asteroids or comets. It's as if the material itself is fundamentally different. Harvard's Adam Hibbard ran the orbital calculations. If 3 iAtlas fired thrusters to change course by just 10 to 15 kilometers per second in September, it could redirect its trajectory to collide with Mars. Natural outgassing from ice sublimation can only provide about 400 meters per second of velocity change. The numbers don't add up unless something else is providing thrust. The timing window matters. 3 iAtlas reaches perihelion on October 29th at exactly 11:44 UTC. That's when it's hidden behind the sun from Earth's perspective. The perfect moment for what Loeb calls a reverse solar Oberth maneuver. A technique where a spacecraft uses the sun's gravity well to break and remain bound to our solar system instead of continuing into deep space. Mars isn't the only surveillance post. Europe's Mars Express orbiter carries the high-resolution stereo camera. China's Tianwen-1 has the higher-RIC imager. The UAE's HOPE spacecraft wields the Emirates Mars ultraviolet spectrometer. 3 nations, 3 different instruments, all focused on the same 29 million kilometer gap between Mars and our mysterious visitor. What they're looking for goes beyond size measurements. If 3I Atlas is natural, it should start developing a proper comet tail as solar heating intensifies. Water ice should begin sublimating at distances closer than 3 astronomical units from the Sun. The object reached that threshold August 16th and still shows no significant water vapor production. Instead, it's producing that carbon dioxide fog Webb detected. But here's the problem. CO2 sublimation requires much higher temperatures than water ice. Either 3I Atlas formed in an unusually warm environment, or it's made of materials that don't match our comet formation models. The trajectory tells its own story. 3. I Atlas didn't come from just anywhere in the galaxy. Kinematic analysis published in the Astrophysical Journal traces its path backward through space. The velocity signature suggests it originated from our galaxy's thick disk, a population of ancient stars formed 9 to 13 billion years ago during the Milky Way's period of intense star formation. If confirmed, 3. I Atlas would be the oldest object humans have ever observed up close, older than our solar system by billions of years, an artifact from cosmic noon when galaxies were young and star formation rates peaked across the universe. But thick disk objects should be metal poor and iron depleted. Instead, 3I Atlas shows that anomalous nickel signature. Nickel without iron appears in human-manufactured alloys, not in natural cosmic processes. It's as if someone separated the metals deliberately. The October 3rd encounter offers multiple observation angles. While Mars spacecraft image from 29 million kilometers, Earth-based telescopes provide simultaneous parallax measurements. The European Southern Observatory's Very Large Telescope in Chile, the Gemini Observatory in Hawaii, radio telescopes that can penetrate the sun's glare, all synchronized to triangulate 3. I Atlas's exact position and motion. Phase angle measurements become crucial. As the object passes Mars, telescopes can observe how its brightness changes at different illumination angles. Natural rocks show predictable scattering patterns. Manufactured surfaces reflect light differently. The phase curve data could distinguish between geological composition and artificial materials. If 3I Atlas is technological, Mars approach might trigger responses. Hidden antennas could begin transmitting. Concealed sensors might start scanning the red planet. The object could deploy smaller probes too small for Earth telescopes to detect, but visible to Mars orbiters at close range. Loeb's calculations suggest a precursor probe scenario. If 3. I Atlas released a small reconnaissance craft earlier in its journey. That miniature explorer could reach Mars days or weeks before the main object. Mars Reconnaissance Orbiter's high-rise camera has the resolution to spot anything larger than 100 meters across. The electromagnetic signature matters too. The UAE's HOPE spacecraft carries spectrometers designed to study atmospheric composition. If 3I Atlas emits any artificial signals, radio transmissions, laser communications, exotic particle emissions, HOPE's instruments might catch them during the close approach window. Temperature measurements add another clue. Natural comets heat up predictably as they approach the sun. Sublimating ice creates cooling effects that balance solar heating. Artificial objects made of metals or composites would show different thermal signatures. The thermal emission imaging system aboard Mars Odyssey could detect those differences. Then there's the debris field possibility. If 3I Atlas is artificial and ancient, it might be shedding components as it travels. Micrometeorite impacts over billions of years could have stripped away outer layers, revealing internal structure. Dust analysis from Mars orbiters might find manufactured particles instead of natural ice grains. The October 3rd window lasts exactly 6 hours. From 4 a.m. to 10 a.m. UTC, Mars and 3I Atlas maintain optimal viewing geometry. After that, the object continues toward perihelion, disappearing into solar glare for 40 days. By the time it emerges in December, it'll be racing outbound toward interstellar space, never to return. Mission planners face resource constraints. Mars orbiters weren't designed for comet hunting. Slewing telescopes to track fast-moving objects consumes fuel and disrupts primary science operations. Each observation of 3I Atlas costs time that could be spent studying Mars geology or atmosphere, but the scientific payoff is enormous. If 3I Atlas proves natural, we've discovered the oldest comet on record. A pristine sample from the galaxy's youth preserved in interstellar cold storage for billions of years. We learn about planetary formation in environments completely unlike our early solar system. If it proves artificial, everything changes. We've detected active alien technology crossing our solar system. The implications cascade through every field of human knowledge: astrobiology, planetary defense, SETI, philosophy of mind, theology, international relations. The October 3rd observations could mark the day we learned we're not alone. Ground truth comes from multiple independent confirmations. Mars Express images correlate with Mars reconnaissance orbiter data. Chinese Tianwen. 1 observations verify American findings. UAE Hope spectrometer readings. Cross-check European results. No single nation controls the discovery narrative. The backup plan involves Jupiter spacecraft. In March 2026, 3I Atlas passes just 54 million kilometers from Jupiter. NASA's Juno orbiter gets another close look. But by then, the object will be 5 astronomical units from the Sun, cooling rapidly, activity declining. Mars in October represents our best shot at peak observation conditions. Weather on Mars could interfere. Dust storms occasionally engulf the entire planet, blocking optical observations, but radar and infrared instruments can penetrate atmospheric dust. The electromagnetic spectrum provides multiple observation channels, even under adverse conditions. Communication delays matter. Mars lies 13 light minutes from Earth during October. Commands uploaded to orbiters take 13 minutes to arrive. Status updates take another 13 minutes to return. Real-time control is impossible. Observation sequences must be programmed in advance based on predicted positions. Trajectory uncertainties compound over time. 3. IATLAS's position is known to within thousands of kilometers now, but small errors amplify during the high-speed Mars approach. Course corrections might place the object slightly outside initial observation windows, requiring rapid reprogramming of spacecraft instruments. International cooperation becomes essential. NASA controls Mars Reconnaissance Orbiter. ESA operates Mars Express. China manages Tianwen-1. The UAE runs HOPE. Scientific protocols must coordinate observation timing, data sharing, and publication agreements before the encounter window opens. Private telescopes join the effort. SpaceX's Starlink satellites carry cameras that could image 3I Atlas during Mars approach. Commercial space companies with Mars assets might contribute observations. Citizen scientists with advanced equipment attempt independent confirmations. The data processing challenge is massive. High-resolution images from Mars orbiters generate terabytes of information. Spectroscopic measurements require complex calibration. Cross-correlating observations from multiple spacecraft and wavelengths demands supercomputer analysis. Results might take months to fully process, but preliminary findings come fast. Within hours of closest approach, raw images show whether 3I Atlas develops the expected comet activity. Brightness measurements indicate if the object behaves like natural ice and rock. Spectral signatures reveal if the composition matches theoretical predictions. The October 3rd timeline compresses years of theoretical work into 6 hours of hard data. Either we confirm our understanding of interstellar objects, or we confront evidence that challenges fundamental assumptions about what travels between stars. Alternative scenarios multiply. 3. I-Atlas could be a hybrid, partially natural, partially modified by ancient alien engineering. It might be a derelict spacecraft billions of years old, its technology long dormant but still detectable. It could be a von Neumann probe designed to study star systems and transmit data back to distant creators, or it could be something completely unprecedented. An artifact from an extinct civilization, a repository of information encoded in crystalline matrices, a warning beacon left by an advanced species. The October 3rd observations provide our first real chance to distinguish between these possibilities. Risk assessment enters the calculation. If 3I Atlas is technological and active, its close approach to Mars might not be coincidental. The object could be studying human activities on the Red Planet, Perseverance rover operations, Ingenuity helicopter flights, signs of potential terraforming or colonization efforts. Defensive measures seem premature but not impossible. If 3I Atlas proves hostile, Mars offers limited protection options. The planet lacks significant magnetic shielding. Atmospheric density won't stop high-velocity projectiles. Our handful of orbiters and rovers represent sitting targets for any advanced technology, but hostile scenarios require impossible assumptions. Any civilization capable of interstellar travel possesses energy resources that make planetary conquest irrelevant. They could harvest power from stars, mine asteroids, synthesize any materials they need. Earth and Mars offer nothing, and interstellar species couldn't obtain more easily elsewhere. More likely, if 3I Atlas is technological. It represents scientific exploration by beings as curious about us as we are about them. The close Mars approach becomes mutual first contact. They study our robotic presence on the Red Planet while we study their emissary from the stars. Communication attempts seem logical. If 3I Atlas responds to artificial signals, that confirms its technological nature immediately. Mars orbiters could transmit mathematical sequences, prime numbers, atomic constants, musical compositions. Any response proves intelligence, but the communication window is brief. Light-speed signals take 3 minutes to travel from Mars to 3I Atlas at closest approach. Interactive conversations are impossible during the high-speed flyby. Single-direction messages work better than dialogue attempts. The precedent matters for future encounters. 3I Atlas won't be the last interstellar visitor. The Rubin Observatory's Large Synoptic Survey Telescope begins operations in 2025 DERS, designed to detect dozens of similar objects per year. How we handle this first technological contact sets procedures for subsequent discoveries. International law lacks frameworks for alien artifact encounters. Who owns salvage rights to crashed alien technology? How do nations share information about potential threats? What protocols govern attempts at communication with non-human intelligence? The October 3rd observations might force urgent development of new treaties and procedures. Public reaction becomes unpredictable. If Mars observations confirm 3I Atlas is artificial, the announcement reverberates globally. Religious institutions grapple with theological implications. Stock markets respond to technological disruption possibilities. Social media spreads information, misinformation, and conspiracy theories at light speed. Scientific integrity demands caution. Extraordinary claims require extraordinary evidence. Even if Mars observations show anomalous behavior, multiple explanations might apply. Natural phenomena we don't yet understand could mimic artificial signatures. Confirmation requires reproducible measurements and peer review, but time pressure fights against careful analysis. 3I Atlas disappears behind the sun days after Mars encounter. The outbound trajectory offers fewer observation opportunities. Delayed confirmation might mean missed chances to study the most important discovery in human history. The October 3rd observations represent more than scientific curiosity. They could mark humanity's transition from planetary to galactic consciousness. We might learn we're part of a universe teeming with intelligence, technology, and civilizations beyond imagination. Or we might confirm our cosmic solitude. 3. Atlas proves to be just another chunk of ancient ice and rock, remarkable only for its size and trajectory. Either outcome transforms our understanding of existence, intelligence, and our place in the universe. Mars Reconnaissance Orbiter powers up its high-rise camera. Europe's Mars Express adjusts its orbital position. China's Tianwen-1 aligns its instruments. The UAE's Hope spacecraft prepares spectroscopic sweeps. 3 months of preparation compressed into 6 hours of data collection that could change everything we thought we knew about visitors from the stars. The velocity signature raises more questions. When astronomers traced 3I Atlas's path backward through galactic space, they discovered it had been traveling for potentially billions of years before entering our solar system. The object's galactic velocity components place it firmly in what researchers call the thick disk population, stars and objects that formed when our galaxy was young and metal poor. This creates a compositional paradox. Thick disk objects should contain less iron and fewer heavy metals than younger solar system bodies. They formed when the universe had undergone fewer stellar generations, meaning fewer supernovae had scattered heavy elements through space. Yet 3I Atlas shows that distinctive nickel signature without corresponding iron content. Natural cosmic processes don't separate nickel from iron. These metals form together in stellar cores and get distributed together during supernova explosions. Finding isolated nickel suggests either unknown astrophysical chemistry or deliberate industrial separation, the kind of metallurgy that requires technology. Ground-based telescopes contribute crucial data streams. The Very Large Telescope in Chile captures spectroscopic measurements, showing the object's chemical fingerprint changes as it approaches the sun. The Gemini Observatory in Hawaii provides polarization data, revealing how 3I Atlas reflects light differently than known asteroids or comets. Radio telescopes add another dimension. The Atacama Large Millimeter Array in Chile can observe 3I Atlas, even when optical telescopes are blinded by solar glare. If the object emits any electromagnetic signals, intentional transmissions, or electronic leakage, radio arrays would detect them first. But 3I Atlas maintains radio silence. No artificial signals, no technological emissions. Either it's completely natural, its technology is perfectly shielded, or it's powered down and dormant. The October 3rd Mars encounter might change that equation. Proximity could trigger automated responses. Many hypothetical interstellar probes would remain dormant during the long journey between stars, activating only when approaching planetary systems. Mars represents the first major gravitational body 3I Atlas encounters in our solar system. Close approach might wake up sleeping systems. The European Space Agency contributes vital observations through multiple Mars assets. Mars Express carries the high-resolution stereo camera, capable of three-dimensional imaging that reveals surface topology and structure. The ExoMars Trace gas orbiter wields the color and stereo surface imaging system, designed to detect atmospheric chemistry that could apply to comet coma analysis. Coordinated timing becomes critical. All participating spacecraft must synchronize their observations to capture 3 iAtlas from multiple angles simultaneously. This provides parallax measurements that determine exact distance and size, plus stereoscopic imaging that reveals three-dimensional structure invisible to single viewpoints. The observation sequence begins October 1st. Mars orbiters start tracking 3 iAtlas when it reaches approximately 35 million kilometers distance. Initial images establish baseline brightness and coma structure. As the object approaches, image resolution improves while apparent motion across the sky increases. October 2nd brings medium-range observations. The object closes to 32 million kilometers, showing fine details in its dust cloud structure. Spectrometers begin detecting individual gas species in the coma. The carbon dioxide signature strengthens as solar heating intensifies sublimation processes. October 3rd delivers the critical 6-hour window. From 4 a.m. to 10 a.m. Coordinated Universal Time. 3. iAtlas maintains optimal geometry for Mars-based observations. Multiple spacecraft capture images every few minutes, creating time-lapse sequences that reveal how quickly the object's appearance changes. Real-time analysis begins immediately. Automated software aboard Mars orbiters processes images as they're captured, measuring brightness variations, coma size changes, and spectral line intensities. If anything unusual appears, artificial structures, geometric shapes, unexpected emissions, alert protocols notify Earth-based mission control. But Earth receives the data 13 minutes after Mars captures it. Radio signals crawl across interplanetary space at light speed, creating communication delays that prevent real-time intervention. Whatever happens during the critical observation window, Mars spacecraft must handle it autonomously using pre-programmed procedures. The dust analysis provides crucial clues. Natural comet dust consists primarily of silicate minerals mixed with organic compounds and water ice. Manufactured dust would show different compositions: refined metals, synthetic polymers, crystalline structures that don't occur in nature. Spectroscopic analysis can distinguish between these possibilities within hours of observation. Particle size distribution tells another story. Natural sublimation processes create dust grains following predictable size patterns. Lots of small particles, fewer large ones, following mathematical power laws observed in solar system comets. Artificial dust sources might show different distributions, particularly if they result from mechanical erosion rather than thermal sublimation. The anti-tail phenomenon deserves special attention. Hubble's July images showed material extending toward the sun instead of away from it. This violates basic physics unless the object somehow generates artificial forces. Magnetic fields could deflect charged particles sunward. Electromagnetic radiation could accelerate specific materials against solar wind pressure. Both possibilities suggest technology. October 3rd, observations focus intensively on anti-tail behavior. As 3. iAtlas approaches Mars. Does the anti-tail strengthen, weaken, or change direction? Does it respond to the Martian magnetic field? These measurements could distinguish between natural electromagnetic effects and artificial field generation. Temperature mapping adds another diagnostic tool. The thermal emission imaging system aboard various Mars spacecraft measures infrared radiation that reveals surface and near-surface temperatures. Natural ice and rock heat up predictably under solar radiation. Artificial materials, metals, composites, ceramics show different thermal responses that identify their composition. If 3 iAtlas contains significant metallic components, thermal imaging would reveal them as hot spots or heat-conducting regions that warm faster than surrounding ice. If it's entirely natural, temperature patterns should match standard comet thermal models based on sublimating water and carbon dioxide ice. The search for geometric structures becomes paramount. Natural objects show irregular, random surface features created by impacts, erosion, and gravitational settling over billions of years. Artificial objects display geometric patterns, straight lines, circular sections, regular polygons, repeated structural elements that indicate design and manufacturing. High-resolution imagery from Mars orbiters can detect geometric features larger than 30 kilometers across. That's sufficient to identify major structural elements like antenna arrays, solar panel assemblies, or modular construction patterns. Smaller features remain invisible at Mars to 3 iAtlas distances. but 30-kilometer resolution surpasses what any Earth-based telescope can achieve during the October encounter period. Ground-based observations are limited by atmospheric distortion and the object's proximity to the Sun and Earth's sky. Mars provides the only clear view during the crucial perihelion approach phase. Backup observation platforms prepare for contingencies. If dust storms on Mars interfere with optical observations, radio telescopes on Earth continue monitoring for electromagnetic emissions. If 3I Atlas proves too dim for some instruments, longer exposures and image stacking techniques enhance sensitivity. The Jupiter encounter in March 2026 offers a second observation opportunity. NASA's Juno spacecraft orbits Jupiter with advanced instruments designed for magnetosphere and atmospheric analysis. These same tools could detect artificial electromagnetic fields or exotic particle emissions if 3I Atlas carries active technology. But Jupiter lies much farther from the Sun than Mars. By March 2026, 3I Atlas will be cooling rapidly as it races toward interstellar space. Comet activity will decline dramatically. Any temperature-dependent processes, sublimation, outgassing, thermal cycling, will slow or stop entirely. This makes October 3rd, potentially, our only chance to observe 3I Atlas at peak activity levels. The object reaches perihelion October 29th. Just 26 days after Mars encounter, solar heating will be near maximum, driving maximum outgassing and coma production if the object behaves like a natural comet. Fragmentation possibilities add urgency to observations. The interstellar comet 2. I Borisov split apart months after its perihelion passage, releasing smaller fragments that confirmed its icy composition. If 3I Atlas fragments during or after perihelion. Debris analysis could reveal internal structure and composition invisible while the object remains intact. Mars observations could catch early signs of structural instability, brightness fluctuations, asymmetric coma development, or debris trails extending behind the object would indicate fragmentation processes beginning. Early detection allows Earth-based telescopes to focus on fragment tracking and compositional analysis. The biological contamination question enters scientific discussions. If 3I Atlas proves artificial and ancient, it might carry biological materials from its origin star system. Microorganisms, genetic information, or chemical signatures of life processes could survive billion-year journeys through interstellar space. Protected inside the object's interior. Mars orbital observations can't detect biological materials directly, but they can identify chemical signatures associated with life processes. Organic compounds beyond simple hydrocarbons, complex carbon chemistry, or isotopic ratios that indicate biological fractionation would suggest the object carries biological information. Planetary protection protocols become relevant if 3I Atlas shows biological signatures. International space law requires preventing contamination of Mars with Earth organisms and protecting Earth from potential Martian life. Similar protocols would apply to potential alien biological materials, though no formal procedures exist yet. The observation data processing pipeline involves multiple international space agencies working in coordination. NASA processes data from Mars, Reconnaissance Orbiter, and contributes to overall analysis. ESA handles Mars Express and ExoMars Trace gas orbiter information. China processes Tianwen-1 observations. The UAE analyzes HOPE spacecraft spectrometric data. Data sharing agreements enable cross-verification of measurements. If NASA's instruments detect unusual spectral signatures, ESA's different spectrometers can confirm or refute the findings. Chinese imaging data can verify structural features identified in American photographs. Redundant observations from multiple sources prevent instrumental errors from creating false discoveries. Publication protocols require careful coordination. If 3I Atlas proves natural, scientific papers can follow standard peer review timelines. If observations suggest artificial origins, the discovery announcement becomes a matter of global significance, requiring government consultation and coordinated international response. The timing pressure intensifies because 3I Atlas won't return. Unlike periodic comets that orbit our sun repeatedly, interstellar objects follow hyperbolic trajectories that carry them back into deep space permanently. Miss the observation window, and the opportunity disappears forever. Historical precedent guides expectations. 1I Oumuamua departed before detailed analysis could determine its exact nature. Researchers still debate whether it was a natural asteroid with unusual properties, or possibly artificial. 2I Borisov behaved more like a conventional comet, confirming natural origins through standard fragmentation and outgassing patterns. 3I Atlas occupies middle ground between these extremes. It shows comet-like activity through coma production and gas emissions, but the composition and trajectory suggest something unprecedented. The October 3rd observations could place it definitively in either the natural or artificial category. Weather conditions on Mars favor optical observations. October represents late spring in the northern hemisphere, where most orbiters spend observing time. Dust storm season typically peaks during southern hemisphere spring and summer, months away from the encounter window. Clear atmospheric conditions should prevail during critical observation periods. Solar activity monitoring reveals minimal interference expected. The Sun approaches solar maximum in its 11-year cycle, but major flares or coronal mass ejections aren't predicted for early October. Space weather conditions should remain stable during the observation window, preventing magnetic disturbances that could affect sensitive measurements. The psychological impact on research teams grows as encounter approaches. Astronomers who've spent careers studying conventional solar system objects face potential paradigm shift. If 3i Atlas proves artificial, graduate students might witness discoveries that reshape their entire field. Mission planners balance excitement with professional skepticism. Public interest intensifies as mainstream media coverage increases. Science journalists explain the significance of October 3rd observations without sensationalizing preliminary findings. Educational institutions prepare teaching materials about interstellar objects and potential technological signatures. Science museums plan exhibits about the encounter. Amateur astronomers contribute valuable observations despite the object's challenging visibility. Advanced private observatories with professional-grade equipment track 3, Atlas from Earth's surface when possible. Citizen science projects coordinate observations from multiple locations to fill gaps in official monitoring. The countdown enters final phases. October 1st brings last-minute instrument calibrations and orbit adjustments for Mars spacecraft. October 2nd delivers final trajectory updates and observation sequence uploads. October 3rd arrives with years of preparation compressed into 6 hours of data collection that could transform human understanding of our place in the universe. As Mars orbiters align their cameras and spectrometers. 3. Atlas continues its billion-year journey toward a rendezvous that will determine whether we're alone among the stars or whether intelligence has been crossing the galaxy long before humanity existed. The day we learn what's really traveling through the cosmic dark, heading straight for our neighborhood of space and time. Final analysis reveals this much. 3. Atlas's October 3rd encounter with Mars provides our best opportunity to determine its true nature. The observations will either confirm it as the oldest natural comet ever studied, or potentially prove we're not alone in the universe. Either way, we'll never see the cosmos the same again. In March 2026, long after 3, Atlas vanishes beyond the orbit of Jupiter. Researchers still study the data from that critical 6-hour window when Mars became humanity's telescope pointed at infinity, the day we learned what's really traveling between the stars.